Imagine traveling toward the edge of the universe, not the edge of what we can see, not the last galaxy visible through a telescope, the actual edge of reality itself. You accelerate past the Milky Way, past the local group, past galaxy clusters and enormous cosmic voids. You cross distances so vast that light itself would need billions of years to follow you, and still you keep going. Eventually you expect something to change. Perhaps the galaxies stop. Perhaps space becomes empty. Perhaps you encounter some unimaginable boundary, a wall separating existence from whatever lies beyond. But modern cosmology gives us a disturbing possibility. There may be no boundary waiting for you, no cosmic wall, no final coordinate. And perhaps most strangely, asking how large the entire universe is may not even have the kind of answer we instinctively expect. We know the observable universe has a measurable scale. We can estimate the distance to the most remote regions whose light has had time to reach us. But the observable universe is not necessarily the whole universe. It is only the portion of reality from which information has been able to arrive since the early universe. Beyond that horizon, space may continue, and continue, and continue, possibly without end. To understand why, we have to abandon one of the most deeply rooted assumptions in the human mind, the belief that if something exists, it must exist inside something larger. A house sits on land, the land sits on Earth. Earth moves through the solar system. The solar system occupies the Milky Way. The Milky Way exists inside the universe. So what does the universe sit inside? That question sounds natural, but physics does not require an answer. Leonard Susskind has spent much of his career thinking about exactly these kinds of conceptual traps, places where everyday intuition collides with the mathematical structure of reality. His work on black holes, quantum information, string theory, and the holographic principle repeatedly points toward the same warning. Space is not necessarily what it appears to be. It may not be a container in which physics happens. Space itself is part of the physical system, and that changes everything. More than 2,000 years ago, people could ask a similar question about Earth. If you walked far enough in one direction, where would the surface end? For someone imagining Earth as a flat plane, the answer seemed obvious. Eventually there should be an edge. But on a sphere, something remarkable happens. The surface is finite, yet it has no edge. You could walk forever without encountering a boundary. You might eventually return to your starting point, but nowhere would you discover a sign reading, "End of Earth." That distinction between being finite and having a boundary is one of the keys to modern cosmology. The universe could, in principle, contain a finite amount of spatial volume while having no spatial edge at all. Or it could be infinite. Current observations tell us that, on very large scales, space is extremely close to geometrically flat, but measuring perfect flatness is impossible with finite precision. A universe that appears nearly flat across everything we can observe might truly be infinite, or it might be so enormously curved that the curvature is far beyond our cosmic horizon. So science does not currently know whether the entire universe is finite or infinite. That uncertainty is important. But something even more surprising is much better understood. An edge is not required. When Einstein developed general relativity, gravity stopped being simply a force pulling objects through a fixed background. Space and time became dynamic. Matter tells space-time how to curve. Curved space-time tells matter how to move. The geometry itself becomes part of the universe. This means that asking what lies outside the universe can be misleading, because the word outside assumes that there is some larger spatial arena surrounding our own. General relativity does not require such an arena. There does not need to be an external room containing space. Space is the room. And it is a room whose geometry does not have to resemble anything our brains evolved to understand. Consider the expanding universe. A common image shows galaxies flying outward from a central explosion, like fragments from a bomb. It is intuitive, and it is dangerously wrong. The Big Bang was not an explosion from one location into pre-existing emptiness. In the standard cosmological picture, space itself was expanding. Every sufficiently distant region was receding from every other region. There was no known central point from which everything was launched. Take a balloon and draw dots across its surface. As the balloon inflates, every dot sees the other dots moving away. From any one dot, it can appear as though that dot occupies the center of expansion. But the surface itself contains no privileged center. Of course, the balloon analogy has a limitation. A real balloon expands into three-dimensional space, while the mathematical universe does not need to expand into anything external. The surface analogy is useful only because it shows how expansion can occur without a center inside the space being expanded. Now imagine replacing the balloon with all of space. Galaxies are not racing away from a single location. The distances between widely separated galaxies are growing because the geometry of the universe evolves. And suddenly another question becomes uncomfortable. If there was no spatial center to the Big Bang, where did the Big Bang happen? Everywhere. Every region we observe today traces backward toward a hotter, denser cosmic state. The patch of space containing Earth was once part of that state. So was the region containing a galaxy 10 billion light-years away. The Big Bang did not happen at a point that we could theoretically travel toward. It happened to space itself. But there is another trap hidden here. People often hear that the observable universe is about 93 billion light-years across, and conclude that this number represents the diameter of everything that exists. It does not. The age of the universe is about 8 billion years. Yet the most distant regions we can observe today are much farther than 8 billion light-years away because space expanded while their light was traveling toward us. That gives the observable universe a radius of roughly 46 billion light-years in present-day distance. But that sphere is centered on us only because we are the observers. An observer in a remote galaxy would have their own observable universe centered on them. Their horizon would include regions we cannot see, and ours would include regions they cannot see. The observable universe is therefore not a physical bubble with a wall. It is an information horizon, a limit on what can have communicated with us. This distinction becomes especially important in the kind of physics associated with Leonard Susskind. Susskind became one of the major architects of the holographic principle, an idea born from one of the strangest conflicts in theoretical physics, the black hole information problem. When matter falls into a black hole, classical general relativity says it passes beyond an event horizon. To a distant observer, the horizon marks a point of no return. But quantum mechanics insist that information cannot simply vanish from reality. Stephen Hawking's discovery that black holes radiate made the paradox much sharper. If a black hole eventually evaporates into apparently featureless thermal radiation, what happens to the information encoded in everything that fell inside? Susskind became one of the strongest defenders of the view that the information must survive. That struggle helped inspire a radical way of thinking about space. In certain gravitational systems, the information describing a region may be encoded on a lower dimensional boundary. The most precise realization of this idea appears in specific theories such as the ADS-CFT correspondence, developed by Juan Maldacena, where a gravitational theory in a higher dimensional spacetime can be equivalent to a quantum theory defined on its boundary. This does not prove that our entire cosmos is literally a hologram in the popular sense, but it does suggest something astonishing. The dimensional structure of space may not be fundamental. The vast interior world we experience could emerge from deeper quantum relationships. And if space itself is emergent, then asking how big reality is becomes even more subtle. Size is a property defined through spatial relationships. But what happens if those relationships are secondary rather than fundamental? Imagine a network of quantum information with no ordinary distance built into it. Certain parts of the network are strongly connected. Others are weakly connected. From those patterns of connection, something resembling geometry might emerge. What we call nearby could correspond to strong underlying relationships. What we call far away could correspond to weaker or more complicated ones. This remains an active area of theoretical research, not an established description of our universe. But it exposes how fragile our intuitive concept of size may be. We assume distance is fundamental because distance is unavoidable in everyday life. Physics may be telling us otherwise, and there is an even stranger consequence. If the universe is spatially infinite, then no matter how far you travel, there is always more space ahead. That sounds simple until you try to picture it. Most people imagine infinity as something extremely large. But infinity is not an enormous number. It is the absence of a final number. You cannot reach infinity by traveling farther. 1 trillion light years is still finite. 1 trillion light years is still finite. Add as many zeros as you want. You have not moved any closer to infinity in the ordinary sense. An infinite universe would not be a gigantic object with very distant borders. It would be a reality in which borders simply do not exist. Yet infinity is not the only possibility. Suppose instead that the universe is finite but unbounded. Return to the surface of Earth. Its two-dimensional surface has a finite area, but a creature restricted entirely to that surface would never encounter an edge. Cosmologists can construct three-dimensional analogs of this idea. A closed spatial geometry could have finite volume without a boundary, travel far enough in one direction, under an idealized static version of such a geometry, and you might eventually return from the opposite direction. The geometry itself closes. There is no cliff at the end of space because there is no end. This is extraordinarily difficult to visualize because we instinctively try to imagine such a universe embedded inside a higher dimensional space. But mathematically, the embedding is unnecessary. A curved space can be described intrinsically. Its inhabitants do not need access to an external dimension for their geometry to exist. Then came inflation, and the mystery grew larger. Inflation is the hypothesis that the very early universe underwent a brief period of extremely rapid expansion. It was developed to explain several otherwise puzzling features of the cosmos, including why distant regions look so similar, and why the universe appears so geometrically flat. Many inflationary models predict that the total universe extends vastly beyond the region we can observe. Some versions lead to eternal inflation, in which inflation ends in some regions while continuing in others, potentially creating an enormous collection of causally separated regions, sometimes informally described as pocket universes. This is where established cosmology begins to blend into more speculative territory. Inflation itself has strong theoretical motivation, and several of its generic predictions are consistent with observations, especially the nearly scale-invariant primordial fluctuations visible in the cosmic microwave background. But eternal inflation, and the broader multiverse ideas associated with it, remain far harder to test. Leonard Susskind became famous for taking the multiverse possibility seriously, especially in connection with string theory. String theory does not appear to possess just one possible vacuum state. Instead, it seems to allow an enormous landscape of possible configurations, each potentially producing different effective physical laws, particle properties, or vacuum energies. Susskind argued that if eternal inflation populates different parts of this landscape, then what we call the universe might be only one environment inside a vastly larger structure. The motivation was not simply philosophical. It was connected to one of physics' deepest puzzles, why the observed cosmological constant is so incredibly small compared with naive expectations from quantum field theory. Anthropic reasoning within a landscape is controversial, and not all physicists accept that it is the right explanation. But the possibility forces an eerie question. What if the part of reality we call the universe is not merely smaller than the whole? What if the whole is so much larger and structured so differently that the concept of a single global size becomes nearly meaningless? There is another horizon waiting for us in the future. The expansion of the universe is accelerating. The simplest explanation is dark energy behaving approximately like a cosmological constant. If that description remains valid indefinitely, sufficiently distant galaxies will eventually recede from us so rapidly due to expanding space that signals emitted from them will never reach us. Not because they locally travel through space faster than light. They do not. But because the space between us expands in such a way that communication becomes permanently impossible. Our accessible cosmic region would become increasingly isolated. Distant galaxies would disappear beyond our event horizon. Future observers, unimaginably far from now, might see far less of the universe than we do today. This is where Susskind's fascination with horizons becomes particularly relevant. Black holes have horizons. Accelerating cosmological spacetimes can have horizons, and horizons raise questions about information, entropy, and what any observer can actually claim belongs to their physical world. A universe can be enormously larger than the region any one observer can access. Reality may be global. Knowledge is local. That tension runs through modern physics. We want to describe the universe from a view outside it, as though we could stand beyond reality and look down at the whole structure. But there may be no such viewpoint. Every observation is made from somewhere inside space-time. Every telescope receives light that has traveled along particular paths. Every measurement is constrained by causality. We build maps of reality while trapped inside the thing we are trying to map. And now the original question begins to transform. How large is the universe? Perhaps infinite. Perhaps finite, but unimaginably larger than the observable region. We do not currently know. Does it have an edge? There is no evidence for one, and our best cosmological frameworks do not require one. What lies outside it? Possibly the question is undefined. But the deepest possibility is not that the universe is simply bigger than we thought. It is that size itself may not belong to the deepest layer of reality. In several modern approaches to quantum gravity, space-time appears increasingly connected to quantum information. Entanglement may help organize geometry. Black hole entropy scales with area rather than volume. Holographic dualities show that entire gravitational worlds can, in special settings, be described by theories with fewer spatial dimensions. None of this yet gives us a complete theory of our own universe, but it suggests that what we experience as an enormous three-dimensional cosmos may be a higher-level description, much as temperature is a higher-level description of countless moving molecules. A single molecule does not possess temperature in the same way a gas does. Temperature emerges statistically from the collective behavior. Could distance emerge in an analogous way from quantum degrees of freedom? Could space itself be something that appears only when deeper pieces of reality become organized in the right pattern? If so, the question, how big is the universe, may one day sound like asking how many miles wide a computer program is. The program exists. Its structure is real. Its relationships are real. But ordinary physical width may not be the most fundamental property of what it is. And still, when we look into the night sky, space feels overwhelmingly real. The moon is distant. The sun is farther. The nearest stars require years for light to cross the gap. Galaxies require millions or billions of years. Distances are measurable. Geometry predicts observations with extraordinary accuracy. Emergent does not mean imaginary. A hurricane is emergent, but it can destroy a city. A wave is emergent from moving water, yet it can cross an ocean. If space-time emerges from something deeper, it can still be fully real at the scale where we live. The mystery is what lies underneath. For most of human history, the cosmos became larger every time our knowledge improved. Earth was not the whole world. The solar system was not the whole universe. The Milky Way was not the only galaxy. The visible cosmos was not necessarily the entire cosmos. Each discovery removed another imagined wall, and perhaps physics is now approaching the final wall, the assumption that reality itself must possess a familiar geometric size. Maybe the universe is infinite. Maybe it closes on itself. Maybe our observable region is one tiny causal patch inside something unimaginably larger. Maybe space emerges from quantum information, meaning that the vast distances between galaxies are not fundamental ingredients, but consequences of a deeper structure we have only begun to uncover. We do not yet know which picture is correct, but one lesson has survived every revolution in cosmology. Reality is under no obligation to fit inside the mental images that evolution gave us. Our brains learned to understand distances measured in footsteps, horizons reached in days, and objects with obvious surfaces. They were never designed to picture curved three-dimensional space, cosmic horizons, quantum entanglement, or infinity. And yet mathematics allows us to reach beyond intuition, somewhere beyond the last galaxies we can ever observe. There may be more galaxies whose light will never reach Earth. Beyond them may lie still more regions. And perhaps there is no final beyond. No edge, no outside. No place where existence stops and nothingness begins. Only a structure whose full extent no observer can ever see. And if space itself is ultimately an emergent description of something deeper, then perhaps the strangest question is no longer how far the universe continues. It is whether, at the most fundamental level of reality, there was ever such a thing as far at all.